Yeah, so this is the last talk, so I want to say something about the talks so far, and they were all excellent. And well, I'm not really an expert on compact objects in here, and I learned a lot, so yeah, that was very nice. And I was going to thank the organizers for inviting me, but I realized that I'm one of the organizers. I'm thanking the real organizers for inviting me to speak here, and I really want to thank them. It's been a very nice conference. Now, so I was invited to give a talk, and I did some work on black holes and so on, but well, some of my work has been presented already by Paolo, and so I decided to talk about something not really specific to gravity, but it was motivated by studying quantum gravity. So I think I have some excuse to talk about this in this conference. So this is about the relationship between Hamiltonian and Lagrangian perturbation theory. So if you have learned quantum field theory or even quantum mechanics, perturbation, well, maybe that's not in quantum mechanics. If you learn the quantum field theory in if you learn quantum field theory, then it's all done in Lagrangian form. And so, of course, basically no interesting theory can be solved exactly, so you have to resort to perturbation theory. And then in perturbation theory, you usually use Lagrangian. The Hamiltonian perturbation theory, so perturbation theory starting from the Hamiltonian is not used very much. But if you start using the Hamiltonian perturbation theory, you realize that actually the Lagrangian and Hamiltonian perturbation theories are quite different, but you have to reach the same result. Of course, they are both valid perturbation theories. So I was interested in why they are equivalent basically. So that's basically about this talk. Sorry, that's basically this talk is about. So first, well, actually, I already talked about some motivation, but I will repeat that. And this is really turning into a guest lecture in maybe quantum field theory course or even quantum mechanics course. So I start with the free theory, which is the harmonic oscillator quantum mechanics, which I think everybody basically knows. Then I go into perturbation theories with no time derivative but interaction, like phi to the fourth theory or something like that. And so actually in those theories, if the interaction term contains no time derivative, then those two perturbation theories are equivalent. And then I'll talk about perturbation theory with one time derivative interaction, in which you see there are some differences. And then if I have time, I'll talk about the case where there are two variables with time derivatives. Very briefly. Then I'll make a concluding remark. Okay, so the motivation, so perturbative quantum gravity is used for studying, for example, inflationary universe. And so I've been doing some work on that. And usually, as I said already, the Lagrangian perturbation theory is used in most calculations. And there's a reason for that. The Lagrangian is covariant. But Hamiltonian obviously is energy in the usual flat space, so it's not covariant. So it's not very advantageous to use Hamiltonian perturbation theory. So people usually use Lagrangian perturbation theory. But in some contexts, you have to use Hamiltonian perturbation theory, and I guess, to justify giving this talk in this conference. For example, the Hartle-Hawking state, what's called Hartle-Hawking state in quantum field theory in short space-time is a thermal state. So, as you probably know, thermal state is a static ensemble, statistic ensemble with this weight, and obviously Hamiltonian is appearing. So you have to use, in principle, Hamiltonian perturbation theory to discuss sort of quantum interacting aspects of quantum theory in the space-time. And well, this and also if there's some conceptual issues are better treated in Hamiltonian perturbation theory. So, for example, you don't have to know anything about this, but just words. Infrared divergences in so-called Pareto of close propagator can be studied using Hamiltonian perturbation theory. So, there's some motivation in studying Hamiltonian perturbation theory. Although it's not covariant, it's not very nice. And now, if you look at most textbooks, the standard, well, what they do is really weird, I would say. They start from Hamiltonian perturbation theory because the thing is the time evolution is obviously governed by Hamiltonian, so you are led to use Hamiltonian perturbation theory in the beginning, and so the standard formula for the Hamiltonian perturbation theory is derived in this in textbooks, and then as I said, this Hamiltonian standard formula for the Hamiltonian perturbation theory is derived in theories with interaction terms containing no time derivatives. So that's 5 to the 4 and things like that. And as I'm repeatedly saying, if interaction terms, so interaction terms in Hamiltonian and Lagrangian theories are identical if there is no time derivative. So then what people do, or what textbooks do, is they keep using this formula actually derived in Hamiltonian perturbation theory, and they just use that interaction term in Lagrangian perturbation theory even when there are interaction terms with time derivatives. So that's what is usually done, and this is sort of motivated by so-called path integral, but somehow it was sort of done in a way which is not explained very well. Now, so as I said, they import the formula for the perturbation theory in Hamiltonian perturbation. They import the formula in Hamiltonian perturbation theory into Lagrangian perturbation theory without sort of without really, in a way, explaining why. And the thing is that, and I'll explain what these words mean shortly in a simple model. But the thing is that the interaction terms are actually different in Hamiltonian and Lagrangian perturbation theories if they contain time derivatives, as I will explain in a simple model. And so the question might be, how can they be the same? And there's one subtle difference in the so-called propagators, which is the time-ordered products of quantum variables. So in these perturbation theories, the propagators are slightly different in some sense. So since they have to give the same results, the logical conclusion is that somehow, although interaction terms are different, because of this subtle difference in the propagator, they must give the same result. So, and I'm sure people are aware of this, but somehow it's not said anywhere in general terms. So what I think what people do is they are somehow aware of this fact in some specific models, and they don't really articulate that. So this equivalence owing to the subtle difference in the propagators in general context. So, so I want to sort of explain in this talk how this equivalence comes about in quantum mechanics actually. So the logic reduces to quantum mechanics really. So I use quantum mechanics of one variable to explain this equivalence, and that's the aim of this talk. Okay, so before going into that, so to convince you that there are some important theories with time derivative interactions. For example, if you look at alternative quantum gravity, then Lagrangian density is proportional to this quantity. And usually what you do is you expand it, you separate the metric into the background metric and the perturbation. And well, there is some integration by parts in Lagrangian and so on, but after that, there are interaction of the form, for example, like this. So all indices are contracted. And if you look at these two derivatives and contraction, there is bound to be time derivative. So among this term, time derivatives are hiding. So there are interaction with time derivatives. And very common, very well-known theory with time derivative interaction is actually scalar QED. So the kinetic term in scalar QED is like this. So phi is the charge scalar field, and A is the electromagnetic field. And again, there's this contraction of mu here, and there is a time component obviously hiding here. So there's an interaction term, for example, this time that, which is among them, there is a time derivative here. So there are theories with time derivative interaction. Okay, so as I said, I start very gently with things everybody knows. So I looked at the harmonic oscillator. And in classical theory, the Lagrangian for the harmonic oscillator is like this. And so I'm repeating two equations, but I meant to set m to 1. So actually, I was meaning to write 1 over 2 q dot squared minus omega squared q squared. So this is the, so m is 1, sorry. So this is the free Lagrangian for the harmonic oscillator. So this is the free theory Lagrangian. So I will start from that. And the canonical conjugate momentum is the partial derivative of the Lagrangian with respect to the time derivative of the quantum variable of the dynamical variable Q, and that's Q dot with M equals 1. Then you know, as you know, that in Heisenberg picture, the quantization condition is that Q and P, the commutator of Q and P is equal to I. Well, I'm setting H bar to 1. So the commutator of Q and P is 1, and P is equal to Q dot, so a commutator of Q and the time derivative of Q is I. And in the Heisenberg picture, the quantum field satisfy the classical field equation, so the quantum variable Qt is expanded like that. And A and AWGAM creation annihilation operator satisfying this commutation relation. A commutator of A and AWGAM equals 1. And this is not very important, but at least to see that you know what I'm talking about. Now, and the ground state, which is usually called the vacuum state in quantum field theory, is defined by this formula. So the vacuum ground state is annihilated by the annihilation operator. Now, and in quantum mechanics, it's not so common to look at this thing called 2-1 function, but in quantum field theory, it's a very important object. So, and it is defined in this context, in the model, in the context of this model. The 2-point function is the ground state expectation value of the dynamical variable Qt and the dynamical variable Qt prime, you know, at different time. And it's a very simple object like that in this theory. And the propagator is the time order version of this 2-point function. So it's written like that. And theta t minus t prime is the so-called Higuchi step function. So it's 1 if t1 is larger than t2, and it's 0 if t1 is smaller than t2. So if t1 is larger than t prime, yeah, then this is 0. Yeah, this is 0, and this is 1. So this is the result. So if t1, t is larger than t prime, so t is in the future of t prime, then the operator is ordered this way, and qt in the future comes before the qt prime in the past. And if t prime is larger than t, then the operator is ordered this way. So t prime is in the future in this case, and t is in the past. So in the context of this model, it's actually just just putting the modular sign in this t minus t prime. So that's the propagator. And actually, the explicit form of this propagator is not very important here, but it's nice to know that you know what this is. So that's why I'm just presenting that. Now we are interested in the time derivative of this propagator. Since this theta is a step function, so if you differentiate that with respect to time, then you get a delta function. So if you differentiate the step function theta t minus t prime by t, then you get delta of t minus t prime. And if you differentiate this with respect to the other argument, then you get minus delta function. So you can study the time derivative of the propagator. And in this notation, this bracket without any zero is actually time order product. So this is a propagator. So time ordering is hiding here. So when you differentiate with this with t, then there are terms obtained by just differentiating these qt inside the time ordering. But there are terms which is obtained by differentiating this Heaviside step function. And in this case, you get this expression, and this needs to be turned into the commutator. But since in this case, the commutator, well, okay, here delta function is of course peaked at t, which is equal to t prime. So delta function is non-zero only when t equals t prime. So you can set this t prime to t, and qt commutes with qt obviously. So this term goes away. So yeah, so this is explaining that. So if you just differentiate this propagator once, then it's the same thing as just differentiating the dynamical variable inside the propagator. And same here. So if you differentiate with respect to t prime, you get the same sort of expression. But the difference comes when you differentiate this twice. So let's, I'm sorry, this is misprinted. So this should have been qt prime rather than t prime t. So this should have been qt prime. Okay, so this, again, sorry about misprint. So this is qt prime. So this is, and also actually in general, we derive this formula. So if you differentiate a time order product of AT and BT prime, then there's a term which is obtained by just putting just differentiating the first this one with time, and also here you get the commutator of AT and BT at the same time multiplied by the delta function t minus t prime. Now, so if we have this result, so if you differentiate this result with respect to t, so you differentiate the original propagator with respect to t and t prime, then yeah, so we are differentiating this with respect to t. Sorry. Okay. Using this formula, you get this result. So this time, there's something non-trivial. So this time, you get the result obtained by simply differentiating t and qt and qt prime with respect to t and t prime. So that's this one. But here you have this term, and as we have seen, the commutator of qt and q dot t. The thing that this delta function puts this t prime equal to t. So no, it doesn't. Sorry. Oh, it does. Sorry, it does. It does. So this basically delta function changes this commutator into the equal term commutator, and we know that the equal term commutator is just I. Therefore, if you differentiate the time order product from outside in some sense with respect to time, then in addition to the term you expect, which is this expression, which is obtained by just dot above q. But there's this additional contribution, which is I times delta p minus p prime. And that's basically the most important formula in this talk. So this is really important. Okay, and I didn't tell you in the beginning, but people use the so when people encounter this expression in the Lagrangian perturbation theory, it's kind of people take it's obvious that the time derivative should act from outside, and that's actually justified in various ways. But like if you don't do that, there's no covariance and so on. But in my view, it's not so clear how to justify it. But in any case, in the Lagrangian perturbation theory, the propagator is differentiated from outside of time ordering if you encounter expression like this. But the propagator in Hamiltonian perturbation theory is different. The time derivative is inside the time ordering. So, in other words, a propagator of q dot and q dot t prime in the Lagrangian perturbation theory is in the Lagrangian perturbation theory is equal to the same quantity in the Hamiltonian, not same quantity, but quantity corresponding to that in the Hamiltonian perturbation theory plus I times delta t minus t prime. So actually the nice way to encode this fact is that the dynamical variable in the Lagrangian perturbation theory, the time derivative of the dynamical variable in the Lagrangian perturbation theory is actually the time derivative of the Hamiltonian perturbation theory plus some mysterious field alpha t, which has this propagator. So propagator of alpha t and alpha t prime is just I times delta t minus t prime. So that's a nice way to encode this relation. Okay, so that's something you need to keep in mind to follow this talk. So this is the difference between Lagrangian and Hamiltonian perturbation theory in dealing with the propagator. So Lagrangian, the time derivative of dynamical variable in Lagrangian perturbation theory has some extra bit with this propagator. So that's the main message here. Now we have to talk a bit about, or review a bit about perturbation theory, how we do perturbation theory in this context. And in quantum field theory, in quantum mechanics is not so important somehow, but in quantum field theory, it's important to find the following quantity in an interacting field theory. So, well, I forgot to mention the interaction here. So this was the original Lagrangian with the chemical one. And I put this interaction term, for example, something proportional to QQ. And this interaction term is not very nice in various sense, which some people would know, but in perturbation theory, it's okay to do that just for the purpose of explanation. Right, so in perturbation theory, in quantum field theory, it's important to calculate this quantity. So since there's an interaction, the field is not, Heisenberg field is not a nice expression we've seen before for harmonic oscillator. It is something very nasty and unknown. But we can calculate the time order product of Heisenberg operator, which satisfies the full nonlinear equation. The string of Heisenberg operators like this, time order evaluated in the true vacuum state. So this is a true ground state, like that. And then in perturbation theory, this quantity, the endpoint function, is obtained by the time order product of free field operators. So free field operator, which has this nice formula like this, and then exponential of this expression here. So anyway, so this is endpoint function in this theory with this perturbation in this perturbation. So you can write this endpoint function in exact theory using this formula, and this C means connected, and I'll explain what connected means in some shortly. And then this exponential has to be treated perturbatively. So exponential should be really treated as this power series, like that. So then if you just truncate the exponential at, say, second order or first order, then this is just a nice polynomial, integral of the polynomial. Okay. Right. So for example, just to give you an example, the for example, 2-point function in the true theory is written in perturbation like that. So, so this I minus I squared and 1 over 3 factorial squared comes from this thing. So you have oh, I'm sorry, this should be n equals 0 to infinity. So if you substitute actually 2 here, so n equals 2, so 1 over 2 factorial this square, and the interaction term is that. So 3 factorial square comes out because you're squaring this, and 2 factorial is in there, and minus a square is there as well, and actually I forgot in this formula lambda square, so actually there's a lambda square here. But anyway, the second order term of this thing is this quantity. And this is a nice, not nice, but this is just a polynomial, so we know the propagator, and there's this thing called Wick's theorem, by which you can just expand, for example, this expression containing 4 dynamical variables into just sum of products of propagators. So, so the rule is that if you to compute this time order product, you just consider all possible pairings of these 4 variables. So, for example, you just in this one you pair QT1 and QT2 and QT3 and QT4, and you pair QT1 and QT3 here, and QT2 and QT4 there, and finally you can pair QT1 with QT4 and QT3, sorry, QT2 and 3. So this enumerates all the possible pairings, and this time order product is equal to this sum of products of a time order product. So then this procedure generalizes to products of more variables. So anyway, there's a way to calculate this time order product. And for example, if you want to calculate the 2-point function in this way, variable t, qt, t at t1 to tau1, and another variable at t2 to tau2, and you are pairing the remaining 2 dynamical variables at tau1 and tau2 here and here. So this one is represented in a similar way, like that. And the statement that says that it has to be connected, so means that the formula, well, the term corresponding to this formula shouldn't be included. So that's not very important, but that's a fact, so I'm just telling you that. Now, so this is, right. So if the interaction is like this, then there is no time variable, time derivative variable contained in the interaction term. Now, the Hamiltonian is obtained in the usual way, so you define the canonical conjugate momentum by differentiating the Lagrangian with respect to q dot, and you get q dot as before. And then the Hamiltonian is defined by p q dot minus L, and you just have to express everything in terms of p and q rather than q dot, and you get this result. And this is this corresponds to the free part of the Hamiltonian. So and this part is the same as the Lagrangian interaction term. So the Hamiltonian, so we call this term with a plus sign interaction Hamiltonian. So the interaction Hamiltonian is the same as negative of the interaction Lagrangian. So in this case, that's true. As I say here, and it's okay to just say, okay, so this endpoint function is in the Lagrangian perturbation theory written this way, and also this is written in the Hamiltonian perturbation theory this way. So they are basically identical. So in this case, the perturbation theory is really identical. But let's at least discuss the perturbation theory with one-time derivative. So, for example, this is a good example. A general sort of Lagrangian with one-time derivative. So you have the free theory part and the interaction term with q dot, which looks like q dot times fq, where f is general function of q, and some potential which depends only on q. And the interaction Lagrangian, or the negative of the interaction Lagrangian, is just negative of this part. And now the problem, not the problem, but the new feature is that canonical conjugate momentum is different from q dot, because q dot appears also here. So the canonical conjugate momentum P is q dot minus fq, where fq is some some function of q. And if you calculate the Hamiltonian in the usual way, pq dot minus L, you get this result. Well, and So this is the interaction Hamiltonian. So this is the free part of the Hamiltonian, and this is the interaction term of the Hamiltonian. And so this is a comparison here. So the interaction Lagrangian, so negative of the interaction Lagrangian is just this by definition, and then from that you find the interaction Hamiltonian, and we got this. And now the thing is that in perturbation theory, the quantum operator appearing in the interaction term are just free operators. So you are supposed to say that P is actually Q dot in the interaction term. So these are then identical, and there's this extra term appearing here because of the fact that we have time derivative interaction. So there's a difference between the interaction term in the Hamiltonian perturbation theory and the negative of the interaction term in the Lagrangian perturbation theory. So the difference is 1/2 fq squared, where fq was the sort of fq was multiplying q dot. Okay, so just then the observation is that actually this extra term comes out of the comes out from the fact that the propagator in the Lagrangian perturbation theory has this extra bit with this propagator, because of the fact that you differentiate the time order product from outside. So the basically the next thing is a crux of this talk. So the puzzle maybe at this point is that how do these theories equivalent when the interaction terms are different? And the answer will be that this should be somewhere else should be in here. So Q dot L is different from the Q dot of the Hamiltonian perturbation theory by this sort of fictitious field with this propagator. Right. So well, I think it won't take that much time from here. So let's go on. Now, so this is the sort of interaction term in this formula for the perturbation theory, and basically, yeah. So then we said that the interaction Lagrangian is equal to that. So you just substitute this here, and right. Then we just write this QL dot as the sum of Q dot, which is for the Hamiltonian perturbation theory, plus some extra bit with this propagator. Then even inside the time ordering, you can use the usual rule of exponential, so you can just separate out this exponential, and then the question is, what does this do? So this is inside the time order product, but still an exponential. So you can just write this as a power series, and then basically using the Wick's theorem, you just pair up these n terms and use the fact that the propagator of A tau and A tau prime is just I times delta tau minus psi prime. So what happens is that if you have integral of alpha f here and integral of alpha f at different time, we can integrate it. So these terms integrated with respect to tau and with respect to tau prime, using the propagator property of alpha g tau and alpha tau prime, these product just turns into this single product because of this delta function property. And using that, basically, I should probably omit all of this thing. You have to do some sort of combinatorics and so on, but the end result is that basically this thing turns into that because of the time order product of alpha operator. So by using that, even though the interaction terms are different in Lagrangian and Hamiltonian perturbation theories, because of the difference in the propagator, you end up with the same same result. So starting from the Lagrangian perturbation theory formula, you can arrive at the Hamiltonian perturbation theory formula because of the difference in the propagator. And you can do that also when there are two time derivatives in the interaction, but probably I should skip that. And it's pretty complicated, but you can do that. And then just to conclude, so I think the calculation was a bit messy and so on, but hopefully I was able to get across the message. So the observation is that if interaction terms contain time derivatives, then interaction terms are different in Hamiltonian and Lagrangian perturbation theory. But the propagators for Q dot t and Q dot t prime are different in these two perturbation theories. And in the Lagrangian perturbation theory, you are using this propagator. In Hamiltonian perturbation theory, you are using this propagator. And the difference is I times the function. So this difference in the interaction terms is corrected in a way by the fact that the propagators are different in the two perturbation theories. And then that makes it equivalent. That makes two theories equivalent. And so my impression is that people kind of know this, but somehow there's no description of this fact in general. So maybe it's nice to generalize this observation from one degree of freedom to field theory or more than one degree of freedom. And also somehow it's kind of strange that somehow the difference in the Hamiltonian Lagrangian perturbation theory interaction terms comes about in a certain way, and then there's this difference in propagator, and it's not very clear why they are related, although somehow in general, by the general argument, these two facts must lead to, let's say, these two facts combined leads to the conclusion that they describe the same theory, but somehow it doesn't seem very natural. So maybe a more natural justification for the propagator in the Lagrangian perturbation theory. So somehow the justification that the time derivative has to be from outside the time ordering in the Lagrangian series. So that fact has to be justified a bit more, a bit better in my opinion. So let me finish with that comment. Thank you.
Very much.
Mateus, pode falar a questão do microfone? Não, não é alta. Não é, um vai usar o microfone e o outro vai usar o outro. Ele já está puxando ali. Então, é essa ordem, é melhor trocar.
Let's have time for questions. Concerns?
So thank you very much for the seminar. Basically the two formalisms are different, but they lead to the same observable consequence.
Yes.
So in this case, my question is, which one is easier to use? Does it depend on the problem?
Lagrangian. Yeah, well, it depends on the problem, but usually it's Lagrangian one. And that's why people use more Lagrangian.
Will it still agree for high order derivatives?
Sorry?
If we consider high order derivatives, will it agree? Also.
Well, all I know would be that if the interaction term is q dot times q dot rather than q dot squared, then yeah, that's an interesting point, I think. So, yeah, I don't know.
Thank you.
Thank you.
Any other question? Okay. So Atsushi, thanks for the talk. And so can you go back a few slides to the yeah, so this alpha equals to n, I think.
Okay.
No, I think the next one.
Oh.
So what happens with the oh right, so yes, what happens with the n equals odd numbers?
Oh yeah, that's a good question. So since alphas have to be paired up, if they are odd numbers, then you can't really pair up. But if you think so, it's zero. So they won't contribute.
Yeah, so I have another question. So I don't know if you have seen this, but there is another way to define the Hamiltonian. So it's not really the Hamiltonian, but it's not PQ dot minus L. It's actually a symmetrized version of that.
I see.
So maybe in this way you have something different.
So the Hamiltonian is different from.
Yeah, because you can define. It's not really the Hamiltonian because the Hamiltonian is actually defined by PQ dot minus L. But there is another way to define a similar function, which basically is supposed to give the same results.
I see.
And it's not PQ dot, it's 1/2 PQ dot and plus something, another thing that I don't recall right now.
I see. So,
But it maybe can give something different in this.
okay, yeah. So that's interesting. I'm really happy. Oh,
Okay. Yeah, to each other.
Yeah, thank
Thank
you.
you. Thank you.
Anyone? If not, then let's thank